EMF, or electromotive force, refers to the voltage created by a battery or by a changing magnetic field. Counter EMF, also called back EMF, is a related phenomenon that we will illustrate in this animation. Here is a simple circuit featuring a battery, a knife switch, and a light bulb. This circuit also contains a wire coil that serves as an inductor. Inductors store energy in the form of magnetic fields that are generated around them when a current passes through them. They are called inductors because they induce a voltage in their coils when that magnetic field changes. We will see this in a minute. The elements in this animation are not represented to scale, and the action we will show in super slow motion actually takes place in the blink of an eye. But this animation is helpful for illustrating how back EMF works. When we power this circuit, the electrons in the current create a magnetic field around the wire as they move through it, as shown by these blue arrows. If the wire is formed into a coil, like this inductor, the magnetic field lines converge in the center. They gradually build up to a maximum magnetic field that is much stronger than the one around the straight length of the wire. Let's watch this again, but this time we'll pay closer attention to what's happening in the wire conductor. In this parallel circuit, the current can travel either through the inductor or through the light bulb. When the current reaches this junction, it splits and flows to both the inductor and to the light bulb. At first, the current flows much more strongly towards the light bulb. This happens because as the magnetic field in the inductor grows, it induces its own voltage through Faraday's law. This is called electromagnetic induction. So the inductor here is creating a back EMF represented by this yellow arrow. Back EMF always opposes the change that created it. So in this instance, the back EMF is opposing the change created by turning on the circuit. It opposes the current. The result, as you can see, is that the back EMF effectively diverts the current away from the inductor and toward the light bulb. This causes the bulb to light up, but only briefly. Once the magnetic field around the inductor reaches its maximum field, the back EMF fades, and the current now favors the path through the inductor because the bulb creates some resistance to the current. The same phenomenon occurs when the magnetic field is shrinking, which happens when we open the switch and stop current flow from the battery. Once again, the back EMF opposes the change that created it. In this case, the change is the cessation of current. So, opposing this change, the back EMF wants to maintain the current, which flows once again to the bulb, causing it to flash before it fades away altogether.